Hey you guys, this is the Chapter 5 Part 2 review. Alright, so starting with number 1, it says, which is not a possible rational root of 10x cubed plus 6x squared minus x minus 4. So the key words here is possible rational roots. So that lets us know we're going to use the rational root theorem. So we're going to identify our constant term, our p, and that's negative 4. And we're going to write all the factors of that constant term. So we have 1 times negative 4, we have negative 1 times positive 4, and we have negative 2 times positive 2. So we have all of them plus or minus, 1, 4, and 2. Then we're going to identify our lead coefficient, our q. All the factors of our lead coefficient, anything that multiplies to be 10, so we have plus or minus 1, plus or minus 10, plus or minus 2, and plus or minus 5. Now to find all of the possible roots, we're going to take each p and divide it by each q. So our possible roots are p's over q are, well, 1 divided by 1 is 1. 1 divided by 10 is 1/10. 1 divided by 2 is 1/2. 1 divided by 5 is 1/5. And notice I said plus or minus for all of them. Now I'll move on to 4. 4 divided by 1 is plus or minus 4. 4 divided by 10 reduces to plus or minus 2/5. 4 divided by 2 reduces to 2. And 4 divided by 5 is plus or minus 4/5. Lastly is the 2. So 2 divided by 1 is 2, and we already have that. 2 divided by 10, that reduces to 1/5. 2 divided by 2, that reduces to 1. And then we have 2 divided by 5, and that is right here. So we already have all of those. So these are all of our possible roots. These are all the numbers we would try in synthetic division. Now our problem asks us which is not a possible root. So we just need to look up above and see which of these numbers is not in our blue box below. So negative 4/5. Come down here, is negative 4 down in our box? Yeah, it's right here. So this one's out. Negative 2/3. I don't see negative 2/3 anywhere in my box, but I should keep checking the other ones. Negative 1/10. That's right here, so I can cross that one out. And positive 1/2, that's right here, so I can cross that one out. So the one that's not a possible root, my answer here is going to be B. Negative 2/3 is not a root. Alright, number 2 says use the rational root theorem to list all possible rational roots of the polynomial equation. So this clearly says use the rational root theorem. So that again is identifying our p, our constant term, and dividing it by our q, our lead coefficient. So our p here is 25, and our q is 5. So factors of our constant term, what multiplies by 25? We have plus or minus 1, plus or minus 25, and then 5 times 5. And for our q, what multiplies by 5? Well, just 1 times 5. So plus or minus 1 and plus or minus 5. So my possible roots are going to be each of my p factors divided by q. So possible roots, to find that, I'm going to say p divided by q. So 1 divided by 1, plus or minus 1. 1 divided by 5, plus or minus 1/5. 25 divided by 1, plus or minus 25. 25 divided by 5, plus or minus 5. 5 divided by 1 is 5, and 5 divided by 5 is 1. So these are all of my possible roots. And this is my answer for question 2. Because it says, do not find the actual roots. Just list my possible ones. So I'm doing the same thing for number 3, it looks like. It says, use the rational root theorem to list all possible rational roots. Again, do not find the actual roots. So we're doing exactly the same thing as before. Our constant term is the term without the x. So our p here is 6. Factors of 6. Well, 1 times 6 and 2 times 3. Our q is the term in front of the highest degree. It's our lead coefficient. So our highest degree is 3, so our q is 1. Factors of 1 is just positive 1 and negative 1. So my possible roots here, again, I'm just going to take each of my p's and divide them by each of my q's. In this problem, I only have one q, or positive 1 and negative 1. So my possible roots is really just my p's here, because dividing by 1 keeps it the same. So 1 divided by 1 is 1. 6 divided by 1 is 6. 2 divided by 1 is 2. And 3 divided by 1 is 3. So these are my possible roots. These are my answers for number 3. Number 4 says a polynomial equation with rational coefficients has the roots 2 plus the square root of 7 and 4 minus the square root of 3. It says find 2 additional roots. So that's all we have to do for number 4 is find 2 more roots. Well, the conjugate root theorem tells us that if we have a square root or an imaginary number, then we'll also have the conjugate. So, one second. Alright, so sorry about that. So, since we have these 2 roots here, all we have to do is change the signs. So, instead of 2 plus the square root of 7, we'll have 2 minus the square root of 7. And instead of 4 minus the square root of 3, we'll also have 4 plus the square root of 3. So it says, find 2 additional roots. Well, these are 2 more roots that this problem would have because of the conjugate root theorem. Number 5 says, a cubic polynomial equation with rational coefficients has these roots. It says, find just 1 additional root. So this is giving us a clue that there's just 1 more root here. Well, 2 over 5, it doesn't have a square root sign, and it doesn't have an I. So it doesn't have its conjugate. However, 3 plus the square root of 11 does. So the conjugate here, we just change the sign, it would be 3 minus the square root of 11. Notice though that 3 doesn't change its sign. 3 is positive, it stays positive. It's just the sign in between that changes. So here's our 1 additional root. Alright, number 6 kind of follows the same lines. It's saying a quartic polynomial. Well, quartic might be a clue. Quartic, remember, is a degree of 4. So a quartic polynomial has these roots, 1 and 4 plus the square root of 15. So it just has these 2 roots listed here. We know we have 4 roots altogether. It says, what do you know to definitely be another root of this polynomial? Well, since we can't see the polynomial, it doesn't actually give it to us. The only thing we definitely know to be another root is the conjugate of this root, since it has a square root in it. And the conjugate of that root is 4 minus the square root of 15. So that's what we know to definitely be another root. The conjugate root theorem tells us that if we have a square root or an I, that we definitely have its conjugate as another root. So if this was like a multiple choice question and it says, what do you know to definitely be another root? Do we know that negative 1 is definitely a root? No, we don't know that it's definitely 1. It could be 1, it's possible, but not definite. Alright, number 7 says, a polynomial with real coefficients has 4, square root of 5, 2 minus 4i, and I plus 3, as 4 of its zeros. All right, so we have 4 zeros already, and they're all listed right here. What is the least possible degree of the polynomial? So saying, what's the least amount of zeros this could have? Again, we can't see the polynomial that it's talking about, so we don't really know. We can just go based off of these 4 zeros it gives us. And again, using the conjugate root theorem, we know that if there's a square root, then we also have the conjugate of it. So that's going to help us out. Notice we have a square root of 5, so we also know we have negative square roots of 5. We have 2 minus 4i, so that means we also have 2 plus 4i. And we have I plus 3, so we know we also are going to have I minus 3. The 4 in the beginning, that doesn't have a square root, and it doesn't have an I, so we don't know that we have its conjugate. We might have negative 4, but we don't know for sure. So the least possible degree, we just add these up. So we got 1, 2, 3, 4, 5, 6, 7. We get 7 zeros. So the least possible degree, my answer here, put in a different color. My answer here is going to be 7. 7's my least possible degree. Number 8. This says, what does Descartes' rule of signs tell you about the real roots of the polynomial? Well, Descartes' rule of signs is when we find the number of positive roots and the number of negative roots. To find the number of positive roots, we write down all the signs of our polynomial. So 8x cubed, that's positive. We have 2x squared, again that's positive. Negative 14x, well, negative. And a positive 5, so positive. To determine the positive roots, we're looking at our sign changes. From here to here, it does not change. From here to here, it does. And yes, we have another sign change. We're always counting up our yeses. So we have 1, 2 yeses, and that means we have either 2 or 0 positive roots. And this is positive real roots. Now to find the negatives, we're going to do the same type of method, but now we have to go and change any of our signs that had an odd degree. So looking back at our polynomial, it's 8x cubed. So 3's our degree and 3's odd. So this first term was positive, but we're going to change it to negative since it has an odd degree. The second term has a degree of 2. Well, 2's even, so it gets to stay the same. It's positive, so it stays positive. The next term has a degree of 1. It's 14x to the first, and 1's odd. This was negative, but since it's odd, we change it to a positive. And our last term has a degree of 0, and that we consider as even, so it stays the same. It's a positive, so we keep it positive. So now we find our sign changes. From the first to the second sign, yes, it changes. Second to third, no. Third to fourth, no. Again, we're always counting our yeses. So we have 1 yes here, which means we have 1 negative real root. So our answer, what does Descartes' rule of signs tell you? Well, it tells us that we either have 2 or 0 positive roots, or we have 1 negative real root. Alright, so number 9. Number 9 says find the rational roots. Okay, so now we need to find any rational roots. And remember, rational, those are fractions, decimals, negative numbers, positive numbers, basically anything except for a square root or an imaginary number. We're going to have all rational roots here. So the first thing we want to do is use our rational root theorem. So the rational root theorem is our p over q. Our p here is the 5, and our q is 1. It's the number in front. So our possible roots, well, factors of 5 are plus or minus 1 and plus or minus 5. Factors of q are just plus or minus 1. So these are our possible roots. So now we have to use synthetic division. So to do that, I'm going to write the coefficients out. The coefficient of 1x cubed is 1. My coefficient of positive 5x squared is 5. My coefficient is positive x is 1. And my coefficient of positive 5 is 5. These are all positive numbers, so I'm going to start with a negative number. I'm going to try negative 1. So my first one, it comes down, negative 1 times 1, negative 1. I add it up, and I get 4. I multiply, I get negative 4. I add, I get negative 3. I multiply, I get 3. I add, and I get 8. So in my does not work column, doesn't work. I'm going to put over here negative 1, so I don't forget that did not work. So I'm going to try negative 5 now. So 1, 5, 1, 5. And bring down the 1, multiply, add, multiply, add, multiply. Alright, and I get 0. So I know that one of my rational roots is negative 5. At this point, I can plug back in my zeros. Now my problem started with x to the third. So when I put back in my zeros, I'm going to start with x squared, and then 1x, and then no x's. So since it's 0x, that's just 0, so it cancels out. So I really just have x squared plus 1 equals 0. When I solve this, I'm going to subtract 1 on both sides. And I get x squared equals negative 1. And then to get rid of the square, I'm going to take the square root of both sides. And when you take the square root, you end up with x is equal to plus or minus I. Well, I is not rational. I is imaginary. My question wanted me to find the rational roots. So I only have one rational root here, and that's negative 5. My other two roots are imaginary. Alright, number 10, find the roots of the polynomial equation. So now I just want to find all my answers. So again, I'm going to use the rational root theorem to find my possible roots. Constant term is negative 2. Lead coefficient is 1. So factors of p, I have plus or minus 1, plus or minus 2. Factors of q, plus or minus 1. So my possible roots here are going to be plus or minus 1 or plus or minus 2. So these are the only numbers I'm going to use in synthetic division. Alright, my coefficients are 1, 5, negative 4, and negative 2. So I'm just going to start with, I'll start with 1. So bring down the 1, multiply, add, multiply, add, multiply, perfect, and I get 0. So I know for one of my roots is 1. And I know I have a total of 3, because my highest degree is 3. So I need at least 2 more. At this point, I'm just going to put back in my x's. I started out with x cubed, so I'm just going to go to x squared, x and no x's. So I have x squared plus 6x plus 2 equals 0. Now to solve this, I can try to factor, or I could use just the quadratic formula. So my a is 1, because it's 1 right here. My b is 6, here's my b, and my c is 2. Now the quadratic formula is x equals opposite b plus or minus square root of b squared minus 4ac. Let me make that a better 4. So minus 4ac. And this is all divided by 2 times a. So plugging this in, I get opposite of b, so negative 6, plus or minus the square root, b squared, so 6 squared, minus 4 times a, which is 1, times c, which is 2, all divided by 2 times a, so 2 times 1. So simplifying this, I have negative 6 plus or minus the square root. 6 squared is 36. And then 4 times 1 times 2 is minus 8. And this is all over 2 times 1, which is 2. Simplifying this some more, I get negative 6 plus or minus the square root. 36 minus 8 would give me 28. And this is all over 2. Now 28, we need to break it down. And 28 breaks down, if we use the border method, then 2 goes into 28 14 times, 2 goes into 14 7 times, 7 goes into 7 1 time. So we have a pair of 2's, so 2 comes out, so I have negative 6 plus or minus 2, and the 7 stays home, since it's not in a group, and this is all over 2. Well, I can reduce that, since the 6, the 2, and the 2, they're all divisible by 2, then I would get, I'll write this over here, dividing each by 2, I'll get negative 3 plus or minus 1, square root of 7, all over 1. So my final answers, going back to my roots, I'm going to take this and I'm going to bring it up to where my roots are. So one of my roots was 1. Another root is negative 3 plus the square root of 7. And the last one is negative 3 minus the square root of 7. So these are my 3 roots. This definitely was a harder problem. I knew I was going to have 3 roots because my degree right here was 3. Alright, 11 and 12 says find all the zeros. So find all the zeros. That's basically just saying find all your answers. So in both of these problems, we have a degree of 3. So we're going to get 3 answers for each one. So for a problem like this, always start off finding your possible roots. So find your P, find your Q. Your possible roots, we have plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. That's because these are all factors of 8. 2 times 4 is 8, 1 times 8 is 8. These are all our P's. Our Q, though, is just 1, so dividing by 1 stays the same. So this is all of our P divided by Q's right here. So these are all the possible roots that we could use. So now setting up my synthetic division, I have 1, negative 5, 2, and 8. And I'm going to start, I'll start with 2. So I bring down the 1, multiply, I get 2. Add it up, I get negative 3. Multiply, I get negative 6. Add, I get negative 4. And perfect, multiply, I get negative 8. So when I add that, I get 0. So 2 is definitely one of my zeros. And I know I have 2 more. At this point, I'm just going to plug back in my x's. So I have x squared minus 3x minus 4. So x squared minus 3x minus 4. And I'm going to try to factor that. I'm thinking to myself, what multiplies to give me negative 4? So what multiplies to give me that, but then adds to give me the negative 3? And that's going to be negative 4 and positive 1. So I can go right into my factors, and I'm going to get x minus 4 and x plus 1. So solving each, I'm just going to take the opposite. So here x equals 4, and then the opposite, x equals negative 1. So those are my last two zeros. So my zeros are 2, 4, and negative 1. So here's my final answer. Alright, let's look at number 12. Number 12, we're doing exactly the same thing. So here, my p is 13, my q is 1. So factors of p are plus or minus 1, plus or minus 13, and divided by 1, it stays the same. So these are my possible roots that I could use, that I could choose from. Okay, so setting up for synthetic division, I have 1, 1, 13, and 13. They're all positive, so I'm going to try a negative number. I'll try negative 1. So 1 comes down, I multiply, I get negative 1. I add, I get 0. I multiply, I get 0. I add, I get 13. And then I multiply, I get negative 13. So that's perfect. It gives me 0 right here. So one of my zeros is going to be negative 1. Now I just need to find my last two, because I know there's a total of 3. So I put back in my x's. It was x cubed, so this is x squared, and this is x. So I have x squared plus 13 equals 0. Well, to solve here, I'm just going to subtract 13 on both sides, and I'll get x squared is equal to negative 13. And then to get rid of that square, I just have to take the square root of both sides. And when you take the square root of a negative number, an I comes out. So x is equal to plus or minus I, and then the square root of 13 just stays the square root of 13. It's not a perfect square, and we can't break that down at all. So our answers are negative 1, I square root of 13, and negative I square root of 13. So here are my zeros. These are my final answers. Alright, numbers 13 and 14, they say what cubic polynomial equation has roots negative 7 and I? So in this problem, you want to write an equation. It's saying which equation, what cubic polynomial equation. So which one has these roots? So we just want to write the equation ourselves. So if it has the roots negative 7 and I, then we also know we have the root negative I. So we're going to write our factors. Since it's minus 7, we'll say x plus 7. Since it's positive I, we'll say x minus I. And then the last one's negative I, so we'll say x plus I. And now we're just going to multiply. We're going to multiply our conjugates first, because with our conjugates, we don't have to do FOIL, we can just do Florida. So it's first times first is x squared, and last times last is negative I squared. Remember, when you see an I squared, you want to cross that out and change the sign. So I squared gets crossed out, and this becomes an x squared plus, and it was 1I squared, so we have x squared plus 1. And then we're going to bring down this x plus 7. Alright, and now we're going to do FOIL. So up here we just did Florida, first times last, and now we're going to do all of FOIL. Alright, so first times first, I get x cubed. Outsides, I get 1x. Insides, I get 7x squared. And last, I get 7. And now I just have to put it in standard form. So my answer is going to be x cubed plus 7x squared plus x plus 7. So this is my final answer. And we're going to do the same exact thing for number 14. So what cubic polynomial equation has these roots? Again, since it's the square root of 7, we also have negative square roots of 7. So my factors are going to be x minus 3, the opposite, x minus the square root of 7, the opposite, and x plus the square root of 7. So first I'm going to do Florida with my conjugates. So first times first, x squared, and last times last, minus 7. And I'm going to bring down the x minus 3. Now I just have to do FOIL. So, first times first, x cubed, outside terms, minus 7x, inside terms, minus 3x squared, and last terms, plus 21. My final answer, I'm just going to make sure it's in standard form. So I have x cubed minus 3x squared minus 7x plus 21. And here's a final answer. Alright, you guys, number 15 is just defining each of the following. So I'm not going to write these out. I'll just talk about them, and you guys can easily look them up in your book or even, on the internet. But the rational root theorem, this allows us to narrow down our options for the numbers that we could possibly plug in to synthetic division to find a root. So the rational root theorem, it narrows down our choices, and it gives us possible roots. The conjugate root theorem, this theorem lets us know that if we have a square root or if we have an imaginary number as a root, then we also have its conjugate, we also have its opposite. But only if we have an irrational number, a square root, or if we have a complex number, an imaginary number. The fundamental theorem of algebra, this tells us how many zeros or roots we have. It says if our degree is 1 or more, then that's how many zeros or roots we have. So if we have like x to the 5th, well, that means we're going to have 5 zeros or 5 roots. And lastly, synthetic division. This is just a process we use to evaluate a polynomial. So it's a process that we could use to evaluate a polynomial. Alright, this last page, it just shows you all the answers. So, check it out. Make sure you got all the right answers. And study hard, you guys. We got a test on Monday. So, not on Monday. On Thursday. Sorry. Tomorrow. We have a test. Tomorrow on Thursday. So study. Come in the morning if you have questions. Email me tonight. elizabeth.bush@ocps.net. Alright, you guys. Have a good one.